In this assessment, we're asked to show how we could synthesize the molecule on the left using the molecules that we have over here on the right. Now, if we were given this problem in a vacuum with all of the reactions in organic chemistry being possible, this would be a much more difficult problem. But we're looking at this one in the context of Claisen and Dieckmann condensations and alkylation of activated methylenes. So knowing that that's kind of the area we're in right now, that's going to make it a little bit easier. I've started, as I always do, by numbering carbons. So first over here on the left, we just numbered them 1 through 8, 1, 2, 3, 4, 5, 6, 7, 8. Looking at, by giving the phenyl group the number 8, that kind of made us believe that this is probably, this group here is going to come from this, where the phenyl is at 8. 7 is a CH2, 6 is a CH2, and it's attached to bromine. So maybe we're going to make some 5-6 bond where some nucleophile displaces the bromide in what would be an SN2 reaction. So we feel pretty good about numbering that. When we took those same numbers and put them here on this hexane diol, we noticed a problem, and that was that there are 6 carbons here, and here there are only 5. So carbon 1, we said, has an oxygen attached, so probably that's carbon 1. And then it goes CH2, 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 3, 4, 2, 3, 4. 5 was a CH, is a CH in the product. It was a CH2, so maybe we're going to remove a proton. But this carbon here is no longer there, right? So we've called that X. Somehow in this reaction, the carbon X must disappear. If we're thinking about the type of chemistry that's going on right now, we might have an idea. Let's see how we could kind of discover that. So working backwards, and we're going to see right away where that carbon must have gone. These reactions, in order to do alkylation of enolates, generally what we want to do is, it's easier if they're coming from an activated methylene. And so probably the last step here is going to be to have done a decarboxylation reaction at carbon 5. And so we can work backwards to this beta keto acid. If we had this beta keto acid, keeping our carbons numbered, this carboxylic acid is probably the one that is X. So this idea of losing carbon X and knowing that we can do a decarboxylation of a beta keto acid makes us believe that this is probably the last step, is to heat this carboxylic acid. Now, how did we get it to be a carboxylic acid? Hopefully we're in the mindset of if we're doing a decarboxylation, then maybe that was a group that helped make a proton more acidic. We can work backwards that this carboxylic acid was probably produced by saponification of an ester followed by an acid quench. And so that would take us back to this particular ester. And I'm going to go ahead and draw it out. So we have, again, keeping the carbons numbered. This is X, that is 6, 7, and the phenyl group is 8. We start to see how we're going to be able to do this now, because having this, if we're working backwards and thinking about how we're going to make the 5-6 bond, carbon 6 has a bromine, so we need carbon 5 to be some nucleophile. Well, good news, if we just draw that out, draw out what would be the best possible nucleophile at carbon 5, what we would draw is the following, where we have a negative charge and a lone pair of electrons on carbon 5. This one is still X. What does this remind us of? Well, this is like an enolate, but it's an enolate in both directions. So it's a pretty stable enolate, a so-called stabilized enolate, which means we can easily make it from the compound with a proton there. So let's draw the conjugate acid of this base. And since we have an ethoxy group here, we can use sodium ethoxide in ethanol to do this deprotonation. So we can deprotonate this molecule, removing the hydrogen at what is C5, to make this conjugate base. Now, what will this base react with? It will react with the alkyl halide, where this is 6, 7, and the phenyl group at 8. So this would do, we said in the beginning that this is probably an SN2 reaction. So this plus the alkyl halide would give us this. Where does this come from? We deprotonate this. So that takes care of using the top molecule up here. How do we make this beta keto ester, and let's keep our carbons numbered, from that diol? Okay, at this point we can almost start to work in the forward direction, because what we see is that in order to make a beta keto ester, this is essentially the Dieckmann condensation. And so if I guess we're going to kind of work forward and backwards. Working backwards, we know that this 1,5 bond would probably form by the reaction of this diester. So let's make sure we have the number of carbons right. There's going to be 1, 2, 3, 4, 5, 6 total carbons. So 1, 2, 3, 4, 5, 6. Draw in that. We'll say that this one is going to be our X. This is 5, 4, 3, 2, 1. What reagents do we need to convert this to this? Well, step 1 is going to be sodium ethoxide in ethanol. And then we have to do an acid quench because of what makes the Dieckmann favorable. We'll always need to do an acid quench at the end of this step. So we get this diester. Now we have all 6 carbons there. We have this hexane diol. How can we get these two to meet up? Well, esters we typically will make from carboxylic acids. We can do a Fischer esterification on both sides. 1, 2, 3, 4, 5, 6. Always make sure we've got the carbons. Never hurts to add the numbers back. This carboxylic acid can be produced from the diol in a couple of different ways. 1, 2, 3, 4, 5, 6. Where that one is X. We can use chromic acid to go directly from the primary alcohols to the carboxylic acids, but we know that chromic acid is pretty toxic and we want to avoid using it. So the other way we could do this is to first do a Swern oxidation, which uses the reagents DMSO and oxalochloride and triethylamine. That would give us the aldehyde, and then step 2, we would do the Pennick oxidation using NaClO2 and sodium hydrogen phosphate. So the combination of the Swern oxidation to make aldehydes and then the oxidation of the aldehydes to the carboxylic acids gives us a slightly greener, a significantly greener way of making the carboxylic acid and would allow us to avoid using the toxic chromic acid. Either way would work, going from the diol to the carboxylic acid to the ester. I didn't put reagents up. Ethanol and sulfuric acid, just the Fischer esterification. Fischer esterification gives us the ester. We do the Dieckmann condensation to make the 5-membered ring. This proton is now acidic, so we can deprotonate it to make an enolate. That enolate displaces the bromide in an SN2 reaction to give this. This ester has now served its purpose to make this enolate more stable, so we can hydrolyze it or saponify it with an acid quench to give the carboxylic acid, and we heat the beta keto ester to do the elimination. In addition to giving us the product, it's going to spit out CO2. So where does that X go? It is in CO2. This rather long video completes the synthesis of the molecule on the left, making use of the molecules on the right.